Is my screen visible?
Yep.
Okay. Okay, so hi, I'm Dhanya. So I'll be now like covering basics of like the memory organization, what you should know, like what are your prerequisites to start learning something called as cache mapping, which Diya will be covering. So first of all, we all started with pipelining. We saw how anything and everything can be done more efficiently. So when it comes to memory, it's all about storing some bits like binary digits. Okay, every end of the day, you're just storing bits in forms of zeros and ones. So you're expected to store like audio files, video files, documents, like every single thing. Okay, but do we have memory for it? Not really, right? So you can't just make your memory so you would just tell that to in order to store all of this, you can try and make the memory unit very big, but that is not practically possible. We will see why as to it's not practically possible. So if you think about increasing your memory size, that means your access time also increases. Access time, I mean, is the time that it takes to go and fetch your data from that memory unit. So that is what your access time is. So as your memory increases, your access time also increases. Okay, so you can't really have a very big memory unit so that you can store everything. Okay, so there are like layers of memories that are there. There are types of memory units that's there. So it's solving different problems that others couldn't, the other memory unit doesn't solve. So that we'll be looking into something called as memory hierarchy in a while now. So, and then something that we have to also know is that our processors are are very fast. Okay, so our memory unit should also keep up with the processor, or else you will just notice that the processor will remain idle the whole time. No, if your memory unit, if you're not able to fetch stuff from your memory unit, that means your processor, which are really fast, stays idle almost the whole time. So there's no use as such. So you should ensure that you design your memory unit in such a way that there is faster access time also. So that is the aim of like actually learning this chapter in itself. Okay. So we'll just see how everything is designed, how the memory units are designed, how each of them turned up, and why each of them is better than the other, and so on. Okay. So okay. Oh my god, this is so annoying. Okay, now we'll look into something like this. Okay, so usually you have your processor and then your memory. Okay, so there's MAR and MDR. We looked into it even before midsense, right? So K address buses. So if there are K address buses, that means there are 2 per K locations, right? This we've already learned about it. And then if the n bit data bus, that means the word length is n bit. So every time a process you access something from the processor, it is accessed in terms of n bits. So your size of the length of the MDR is n bit, and then for MAR it is k bit. Okay, so for k bit address lines, you have 2 per k locations, and then your word length is n bits. Okay, that is just of what this is. So I'll explain you in detail about how this exactly works. So before that, there are some control lines. So that is your read and write operation. So if it is 1, that means it's read, and if it's the w bar, no, so 0 represents the write operation. And then there's something called as MFC, that is called as memory function completed. Okay, so I'll just now explain what each of it is. So how this exactly works. Till now it's clear, right? You can react. Okay. So we just look into this now. So the processor reads data from the memory by loading the address of the required memory location into the MAR register and setting the read or write unit line to 1. So first you're going to talk about the read operation. Okay. So the processor reads data from the memory by loading the address into your MAR. So your address is first stored into your MAR. Okay. So in case of your read operation, and then you're in your control lines, it will be 1 because it is read. No, W bar is 0. So after this is done, the the memory responds by placing the data from the address location onto the data lines and confirms this action by asserting the MFC signal. This is too much words, but essentially what they're saying is after your address from the processor is brought to your MAR and your read signal is initiated, then your memory function completed gets activated, saying my the memory I've actually fetched from the memory and that part is completed. So just letting the device know that the memory part of it is completed. The memory fetching part of it is completed. Okay. So upon receiving the MFC signal, the processor loads the data on the data lines to the MDR register. So once the MFC signal is initiated, then the data is stored in the MDR. So if I need to just brush up this once again, so if you need to read something from the main memory, first the address of that thing that you have to read will store in the MAR. Okay, so and then your read control line is initiated. So if it has to be read, then it will be 1. Okay, 1 means read, W bar is 0. So when your read signal is initiated, then once your read signal is initiated, the MFC will be activated, telling that my memory fetching part is done. Now it's just transferring of data. So after MFC is activated, now whatever data that we have to fetch, it will be go to the MDR. It will go to the MDR. Okay. So that is your data unit, right? So it will go to the MDR and then you will be able to read your data. So that is what the read is. Okay. So when it comes to the writing, okay, the processor writes data into the memory location by loading the address of this location into MAR and loading the data into MDR. It indicates the write operation, that is 0. So it's the same thing. Okay. So wherever you need to write, that address will be stored in the MAR. And then a write signal will be initiated. So 0 will be initiated. So after that, MFC signal will say that I've done this. Then that whatever you need to write, it will be in the MDR. Okay, then later it will get returned into your main memory. Okay, so this is what your entire flow is. Does anyone want me to repeat it? Or is it fine?
This is fine.
Okay, I'll just tell once again, just in case. So first, if you need to read something, the address from the memory will be stored in the MAR. Okay, so then your read signal is initiated, which is 1. Then since your memory fetching part is done, the MSC will be activated. The memory function completed. It will say that your memory function is completed. So, and then that data will get stored in the MDR. So that is what your entire flow is. And it's similar for write with control signal as 0. Okay. So the basic terminologies involved in this would be first is memory access time. So the time between the read and the MFC. Okay, so this is the memory access time. And then memory cycle time is the minimum time delay required between the initiation of 2 successive memory operations. So between 2 successive memory operations, as in I could say between 2 read operations. Okay. So between 2 read operations, the minimum time delay that is required is your memory cycle time. Okay. Then we all know what RAM is. Okay. So any location can be accessed independent of the location's address. So independent of the location's address is very important. So the access time for accessing any data in your RAM is the same. It doesn't depend on the location address. Okay. So that's why it's the random access memory. Okay. So your access time is actually fixed for accessing any particular data in your RAM. Okay. So is this part clear? So the basic structure of how it works and then your basic terminologies. So I'll move on now. Okay. Okay, now we'll be dealing with something called as semiconductor RAM memories. So in like the AIDS PPT, there's like a lot more things that's not necessary essentially. So I'll just be covering the parts that are actually essential. So okay, so semiconductor RAM memories, they are available in a wide range. So their cycle time ranges from 100 nanoseconds to less than 10 nanoseconds. These are all just general definitions, but yeah, we'll be looking into some, we'll be looking into its types also. So SRAM, DRAM, we'll be looking into it. So first, the organization of memory cells. You don't need it as much, but I'll just tell you what it essentially is. So there are like four address lines over here. So if it's four address line, how many locations? Can anyone maybe drop it in chat or something? Uh, there are four address lines. How many locations? Ah, yeah, 2 power 4, right? Okay. Yeah, it's exactly 2 power 4. So that's, I mean, which is 16, no? So there are right lines from 0 to 16. These are your address locations. All right. Is someone typing? Okay, people are typing. But yeah, it's essentially 2 power 4 locations. Okay, we'll move on. So if you see here, okay, if you see here, each row of cell constitutes a memory word, and all the cells of the rows are connected to a common line called as the word line, which is driven by the address decoder on the chip. So based on the address lines, there are 16 word lines. Okay. So the cells in each column are connected to sense or write unit by two bit lines. The sense and write circuits are connected to the data input and output lines of the chip. So it's just how the organization is. So it's connected to two bits and it's connected to the data input and the output lines, the sense and the write units. So what is it going to do? So during a read operation, these circuits sense or read the information stored in the cells selected by the word line and transmit this information to the output data lines. So based on the address, any one of so it's a decoder, right? So we all know how a decoder works. So based on the address lines, any one of these 16 lines will be chosen. So based on that location, the sense or write circuit will detect what that data is and then it will send to the output unit. That is how read works. Okay. So in case of write operation, the sense or write circuits receive input information and stores it in the cells of the selected word. So in case of writing, the input will go into the sense of the sense or write unit and then it gets stored in the exact location. All right. So it's you don't really need this, just the basic gist of it is enough. So in case of write operation, whichever word line is chosen, the data in that will get read or sensed by the sensor write circuit. In case of writing, the input gets stored in the exact memory location. All right. So is this fine? You can react. You want me to repeat something? Yeah, I'll repeat quickly. So yeah, I told you that there are four address lines. So you told me that there are 2 power 4 locations, right? So 2 power 4, which is 16 locations. So when you are writing something, sorry, when you're reading something, that means, okay, this based on that address, any one of these 16 locations will be chosen, right? So the data in that location will be sensed by the sensor right circuit. So that is, you're reading the data that is there. Okay, and it will send to your output lines. So output lines is in the bottom. Okay, so there are from B0, from the bit 0 to B7, it's there. Okay, they're just omitting all of this, just a rough diagram. Okay, so in case of a write unit, whatever input is given here, that will get returned in the exact memory location where you've tried. So these are all flip-flops. So that will get stored in your flip-flops. All right, does that work? Okay. Is everyone else fine with it? Okay. Okay, this is the exact same thing that we discussed. So now we'll be moving to something called a static RAM cell. Okay. So this might seem quite tricky, but this also you need to just understand the gist of it instead of knowing it in detail. I'll just explain what it is essentially. So if you just look at the picture, what can you notice? There are two NOT gates. When did we see this before? We saw it in like digital design, no? A latch. This is how like a basic structure of a latch would look like, where if you give 1 year, it'll be 0, and again it will become 1. So it works like a memory or a latch, no? It just, the data stays within. Okay, so now here your T1 and T2 are your transistors over here. Okay, so it acts as your switch. So based on the word line, okay, there's something called as word line. So based on your word line, this T1 and T2 works accordingly. So I'll tell you how it works. So we'll just see what and all are there first of all. So then there are your bit lines. So in order to read something or you write something in terms of bits, that's here. So when you're writing something, you give the input here, no? So whatever input you give will be overwritten. But when you're reading something, whatever is there in your latch, you're reading it. Whatever is there in your memory unit, you're reading it. Okay. So when you're writing something, whatever you give as your bits, that is your input, and that should overwrite your content that is there in your latch. Okay. So if we see here, if the word line is 0, okay, that means both your transistors, which is connected to your word line, will be 0, no? So that means it will be in off state, right? So if it is an off state, then there's only the cell that is remaining. So that cell is isolated and the contents remain with itself. So the contents stays with it. Okay. So it behaves like a proper latch when the word line is 0. Okay. Is this part clear? When the word line is 0, that means T1 and T2 connected to the word line. So both will be 0. Transistor is 0. That means it is an off state. So in off state, only the cell will be remaining. So whatever the contents in the cell will remain as it is. So it will work like a proper latch. Okay. So let's say when you're, okay, we'll just look into cases also now. Okay, we'll see what is over here. So if the word line goes high, that means read. Okay, when you're reading and your word line goes high. Okay. So B, your bits is 1 and B dash is 0. So B is your essential content that is there in your latch. Okay. So here we have given our content to be 1 and it became 0. So that will be our B. So B dash will just be the complement of B. Okay. So that will store 0. So in case of writing, so whatever, sorry, in case of reading, here it's reading, right? So in case of reading, whatever is stored in the latch will also get reflected in your B and B dash, and that will only be sensed as output, no? Because it's a sense and write circuit. So that will only be sensed as your output. So whatever is your initially your data that you're starting with will be B, and then 0 will be B dash. Okay. So sense line sets output high. So what will sense line sense? Sense line will sense the output. So how does the sense line sense the output is our question now. So if you see the general working of like, if this is your bistable switch as such, yes, it's 0 and 1, no? So it's essentially a bistable switch. Okay. So if you see this 1 and 0 need not be just 1 and 0. It could be 0 point something. Okay. So there's something called as threshold level also, right? So above this threshold level, if it goes, that means it's high. If it goes below this threshold level, it is low. That is 0. That is what we assume in like. So it's not technically 0 or just 1. Okay. So if it is, we are just, if here it is 1 and here it is 0. Okay, so first we'll talk about read. Okay, so if the word line is 1, that means both of the transistors will be on. So your B and B dash will read 1 and 0 respectively. But this essentially isn't 1 and 0. How will we ensure that we read 1 and 0 properly? So probably this could be something like 0.7, while our threshold is some 0.6. And this could be some 0.3. So now we have something called as amplifier. Okay, the sense amplifier. So that will see the difference between these two. So it will see the difference between these two, and then it will tell me, okay, I'll keep this as, wait, I'll keep this as 0.9 and this as 0.3. Our threshold I told was 0.5, let's say. So above 0.5, it will be 1. That it will be like high. Okay. Below 0.5, it will be low. Okay. So if you the sense amplifier will see the difference between these two, 0.9 and then your 0.3, that will be 0.6 and it will be higher than 0.5. So to detect that it is high. Okay. Is this clear? Like I can repeat it once again. Okay. Okay, wait, I'll repeat it once. So we have two NOT gates. That means it essentially is a latch. So your content stays within. Now we have two transistors over here, T1 and then T2. Okay, so it acts like a switch. So it is connected to your word line. So it depending on your word line, this transistor will be either off or on. Correct? So this transistors T1 and T2 are also connected to B and B dash. Okay. So now first condition is when word line is 0. Okay, when word line is 0, that's a very simple case. So if word line is 0, now both your transistors will be 0. That means only the cell unit will be there. Correct? So only this latch will be there and the content stays within. It is not influenced or it just works like a proper memory unit. Okay, a latch. That's all. But now when it's a case when the word line is 1. Okay, and we are taking an example where it is a read. Okay, when we are actually reading something that's there in your latch. What is there in your latch? 1 is there. 1 is the data that you gave initially. That is only being within your latch unit, right? So you have to identify that it is 1 which is staying inside. Okay, with this circuitry that we have formed here. So how is it identifying that it is 1? So your B and B dash is your you have to sense it in your B, you should get your output. That is 1 you should get. So B dash will be the complement of the output, no? So your B should actually read 1. Okay. So how is it reading is the question. Okay. So essentially, usually in your circuits, the 0 and 1 doesn't mean it's like proper ideal 0 or ideal 1. Okay, it is a value that is in the range between 0 and 1. Okay, so there will be a threshold value. Let's assume that it is 0.5. Okay, so ideal threshold value. So above 0.5, it is high. Okay, whatever value above 0.5, it means it's high. If it's below 0.5, that means it's low. Okay, so let's say this 1 isn't essentially 1 but 0.9. Okay, it is still high. Okay, and let's say instead of the 0, it is 0.3. Okay, we are just writing the ideal values, but it is not as ideal as it seems. So in reality, it is some odd values like these. Okay, so how will we read it? So we have to read this 1 to your B, no? So there's something called as amplifier that actually reads this. Okay, so it reads the difference between these two, and then it concludes that a high value is stored. Okay, so 0.6, that is greater than 0.5, their threshold value. So it is a high value. So it'll conclude that 0.6 is stored, that is a high value which is stored. All right. So is this fine now? All right. You need not go into as much details for this. It's fine if you just understood the gist of it. It's just like basic concepts that you need to look into. But yeah, okay, moving on. So whatever I said is just told in terms of words. Okay, but okay, read and write operations is just told in some terms of word. Okay, so in case of write operation, so read, we told what happens. So in case of write operations, so both, let's say your word line is 1, okay? So both your transistors are on and you are entering some value into your B and B dash, okay? So whatever you're entering in your B and B dash will will be your latch values, okay? So the B and B dash will override your latch system because you're writing into the system now. So your B and B dash will take over and that will write the value in your latch. Okay, that's what when it comes to writing. That's all. Okay, this is just the gist of the entire thing that I told. So when I told it is the word line is 0 now, that means it is in latch state. Okay, that means it's in memory state. So no change. So when it is reading and when it is 1 now, it will detect whatever is in B. Okay, when you're reading, it will when you're reading 1, okay, your data is 1. So your B dash will be 1. So your result is you're detecting 1. Okay. So basically you're reading 1. Your data, your initial data that we saw here, this data is 1. So you have to read this. That means your B should be 1. Right? So that's what is over here. Then when you're writing 0, okay, and your word line is 1. Your word line should also always be 1 if you're doing some operation. Else it will be in like normal latch condition. So when your word line is 1 and you're writing 0, that means B dash should be 0 and B should be 0 and B dash should be 1. So you're storing 0. This B and B dash will override your latch condition and you will store 0 and 0 in your latch. Okay, so similarly when you're writing 1, you will actually write this B and B dash will actually override your latch system and it will write 1 to your latch. Okay, so is this part fine? Oh, the reading up or you're reading what is there. Okay. So like writing is you're overwriting the condition. So if the initial condition write up or if initially the latch has 0, but you're gonna write 1 now, it will be overwritten. Overwritten. Okay. That 0 will be overwritten with 1 now. But you're reading now, if there is 1 there, you have to read that 1. So in that case, your B will be 1 and then B dash will be 0. Uh, Wait 1 second. What did you ask? Is there a separate line here to tell me whether I'm reading or writing? I think it depends on the read and write operation. I told you, no, read stands your control lines. So read and write are your control lines. So read means one, it depends on what you choose. If you take your notation as R dash W bar now, then R will be 1 and then your W writing operation will be 0. So it depends on your control lines. Okay. Okay, next. Okay, the CMOS SRAM, no, we don't really like. Okay, before this normal SRAM, no, it takes up, it needs 6 transistors per bit. Okay, so there's a lot of hardware that is required, but it's really very efficient. I'll tell you why it's more efficient. We'll learn about what a DRAM is, so we'll get to understand why it is more efficient than DRAM. But still, you have to know that your hardware cost is a bit more because of the more transistors per bit. Okay, so CMOS transistor. So it's just based on MOSFET concept. So sir told to actually omit this. I've just added to just know to let you know that there is a type called a CMOS SRAM. But yeah, SRAM is also volatile. CMOS SRAM is also. And then low power consumption, no current flows except when being accessed. And then it is also faster access and it's expensive because 6 transistor per cell. I have to look into what's the difference between, I think SRAM is based on CMOS. Okay, it's based on the MOSFET concept, so CMOS SRAM. Okay, then, okay, DRAM. Okay, so from exam perspective, we need to just know what SRAM is, what DRAM is, what is the advantage of SRAM over DRAM. So stuff like that, okay? So we'll just, instead of this random facts, we'll just go into these things, okay? So if you look at the circuit over here, again, you have your bit lines, your word line, and then you have your capacitor, your transistor, and then your capacitor. So capacitor is charged to write a one. Okay, so basically, this capacitor will get charged and discharged, no? So when it is charged, you get to write something or you get to read something. But when it is losing its charge, you need to refresh this capacitor again. So that takes up some amount of time. But, so I'll just read. Okay. So if a read detects a voltage on the capacitor above the threshold, I told you, no, it's the same concept of this threshold. Okay. So here, if it's above the threshold value, then it sees a 1. Okay, above the threshold value, it is considered as 1 and drives the bit line to full voltage and recharges the capacitor. Okay, so if the read detects a voltage on the capacitor above the threshold, it sees a 1 and it drives the bit line to full voltage and recharges the capacitor. Okay, but in case if it sees a value below the threshold value, then it sees a 0. So that time the capacitor will get discharged. Okay, so you have to like keep charging and refreshing your capacitor at times so that you actually function things properly and you get to read and write properly. So that's what the concept of DRAM is. So you have to know, in case of SRAM, there is no concept of capacitors and all. So it remains volatile. This also remains, DRAM also remains volatile. But there it's just transistors and your bit lines and your word lines. And you're not really refreshing something, you're not taking up extra time to do something else. But here, this refreshing your capacitor still takes some amount of time. Okay, so that is your That is why this is not this is not really as efficient as SRAM. But yeah, this only takes up one transistor per bit. But SRAM, it takes 6 transistors per bit. So in terms of hardware complexity, hardware cost, so it's still higher in SRAM. So this is the trade-off essentially. So now to see the difference between them. Okay, I think I've told everything, but let's see. SRAM uses transistor to store a single bit of data that we have seen. DRAM uses a separate capacitor to store each bit of data. All right, this is fine now. SRAM, we use transistors and latches. DRAM, it is based on capacitor. And then SRAM does not need periodic refreshment, but DRAM needs periodic refreshment. SRAM structure is complex than DRAM. Why is it complex? Because of more number of transistors. DRAM structure is simpler, simpler than SRAM. SRAM is expensive. DRAM is less expensive. SRAMs are faster. DRAMs are slower. So SRAMs are usually used in cache memory because it's more faster, and then DRAMs in our main memory. All right. So is this fine? You can react if it's fine. Yeah, fine, Harish. Okay. So now this your SRAM, DRAM, and all, it's in your primary memory, no? So all of this is volatile, is what we know, but it's more effective. So if it's but if you need something non-volatile, then that's why you have your secondary memory. So in your secondary memory, your data remains permanently, okay? But in your SRAM, DRAM, which is essentially your primary memory, so that is volatile, okay? That's just the difference. So now the choice of a RAM chip for a given application depends on several factors. So cost, speed, power dissipation, size of the chip, and so on. That's what the difference between SRAM and DRAM we saw. So static RAMs are generally used only when very fast operation is the primary requirement. So static RAMs, I told it's preferably used in your cache. So only when you require a very fast operation, do you use your static RAMs. Okay, so it is used in your cache memory. Okay, so your dynamic RAMs, it is mainly used in your main memory. Okay, it's a predominant choice for implementing main memories. So yeah, it's just the difference. Okay, moving on to ROM and your types of ROM. We have dealt with this even like last semester, I think. So essentially what your ROM is, it's your read-only memory. It's non-volatile. So if you just see here, like, so your connections determine whether a cell stores 0 or 1. Okay. So if it's not connected to store a 1, connected to store a 0. That's all. Just the diagrammatic representation. But yeah, you need to know that this is actually done while manufacturing itself. So you can't change it later. So it is manufactured that when it is not connected, it is storing a 1. If it is connected, it's storing a 0. You can't really program it. But in case of your programmable ROM, so one time it is actually manufactured and it is all made 0. But if you fuse it, you can change it to 1. So based on you, and then you can do that only once. Okay. So you can fuse it to make it programmable, and you can use it for your applications. Okay. That is your PROM. Then EPROM, EPROM. Okay. That is it. Okay. What is your EEPROM? So it is your erasable read-only memory. So it can, whatever is programmed before, that can be erased using ultraviolet light. Okay. Earlier it was, you're fusing it. Now you can actually fuse it with your ultraviolet light. Okay. So here what do they say? Transistor can have a charge put into that. put into it that causes it to remain permanently open. Okay, so it is designed to be permanently open, and that can be erased using ultraviolet light. That can be programmed or erased using ultraviolet light. All right. Then, okay, electrically erasable PROM, that is cells erasable selectively. So you can selectively erase your cells using, so in your EEPROM, it is UV light, and here you can electrically erase it. Okay. So, and then your flash memory, it's similar to your EEPROM only. So it's like usually used when there is, okay, I'm so sorry, I'm getting distracted. Okay, your flash memory is usually used in your SSDs, USBs and all. Okay, it is similar to your EEPROM. So that's all. We have just done the same thing. Then comes your memory hierarchy. Okay, so this is something that we need to know. So your memory hierarchy, we have looked into your main memory. So we looked into SRAM and DRAM, right? And we concluded that SRAM is better than DRAM. But and then this your main memory is like volatile. So you need you need stuff to store permanently also in your device. So that's why you have your secondary memory. But that is a very your size of your secondary unit is pretty large compared to your main memory. But you need to access things faster. So since I told you, the first thing that we discussed was as memory size increases, our access time also increases. So in order to reduce your access time, you need to reduce your memory size also. Okay, so that is what the idea behind caches. So you have your secondary caches like L2 and L3. There are three types of caches. So L1, L2, and L3. So L2 and L3, it's predominantly off chip. Okay, so that is also pretty much faster. But L1 primary cache is even more faster. So, but the sizes of all of this is very less. Okay. Then you have your registers where that's even more faster and you get to access things much faster also. Okay. So if you see the relation, as you go from your registers to your secondary memory, your size increases. But what your trade-off? As size increases, your speed increases otherwise. Like as size increases, your speed decreases. But if you had to look into this diagram and explain, from registers and your secondary to your secondary memory, the size increases. Okay. But the speed from your secondary memory to your registers, the speed and your cost increases. And your caches and all are not really as much big. So you can ask me, okay, I have a cache, so why can I not make it like infinitely big so that everything can be accessed faster? That is not possible because it's very expensive. So yeah, so your speed and cost increases as we move towards your caches, registers, and so then okay. So main memory is slow in comparison to your processor speed. So main memory constrained by packaging, electronic characteristics, and cost. So just telling that main memory is very slow compared to the processor. So that's why we need something called as cache, because which is 10 times faster than your main memory. Okay. So now we have something called as locality reference. So if you have a program, like you don't tend to like use every single one of it. Like you don't use every single how do I put it? You have, okay, let's say you have like your game or something when you're downloading. No, sorry. Okay, I can't think of an example now. But yeah, so locality. So programs tend to spend their time focused on particular group of instructions, which are loops and frequently called procedures. So sometimes only some part of your program is of utmost importance than your other parts. So, so that part will get access much is tend to get it is tend to get access much more faster and like much more quickly. So if you need to access some part of it, sorry, wait, I'm blabbering. Sorry. So locality reference. You have a program, only some part of it is actually required like more frequently. So you need to have that part of it in your cache or in your in your memory units, which can be accessed faster than your other parts. So that is what we are trying to solve here. So we have two types of locality, which is temporal and spatial locality. So first, temporal locality. So recently executed instruction is likely to repeat soon. So if you're accessing something, there is high chance that you might access the same thing again. So that is what your temporal locality says. So we'll later look into the replacement algorithm. So that time this temporal locality comes into picture. So spatial locality is where instruction near an executed instruction is likely to be executed soon. So let's say you have in your main memory, let's say you have an array from uh, 1 till whatever. We have it till 8 or something. Like A1, A2, A3, still A8, some address. Okay, so in your main memory. So if you're accessing, like say, this is 0 to 9, like your index. So if you're accessing something like 2 over here, so the index with 2, that means there are high chances that you might access something near it. Okay, so what the cache will do is it will actually take up this whole thing and keep it in the cache, saying that when you're accessing this thing which is there in 2, you might bound to access something that's nearby also. So it will take up this whole row and store it in your cache. So that is what your spatial locality concept is about. Okay, so your important part or the parts that you might tend to use frequently that might get stored in your memory units, which whose access time is much faster. Okay, did everyone get till this? Okay, so now I'll be handing it over to Dia. So I'll just stop sharing. I'll
Hello,
be
guys.
continuing. One
Yeah,
second,
yeah, go on, go on.
I'll just stop recording. I'll be continuing after Dia maybe. So now Dia will continue.